Hello, I am Mike Wilbur, a PhD student at Vanderbilt University. Today I'm going to discuss efficient data management for intelligent urban mobility systems. Modern AI-driven urban mobility applications require working with large-scale, multivariate, spatiotemporal data streams from a variety of heterogeneous sources. While research often is performed on historical, static data sets, the implementation of these applications presents unique problems related to data management, processing, and presentation. Current solutions typically consist of ad hoc combinations of open source and proprietary technologies customly designed for each application or set of applications. In this work, we present our own experience in designing a data management architecture for our partner agencies as we implement our various AI research in the real world. We consider this work a jumping-off point as we look to study problems of data management for the next generation of AI-driven urban mobility and smart city applications. The problem of data management within this domain inherits all of the problems of velocity and volume associated with large-scale streaming IoT systems. Additionally, the data itself is highly heterogeneous, as domain-specific schemas are used for each class of devices. For example, MDS for scooters or real-time GTFS for transit feeds. The data is also spatial, which presents problems of data retrieval and data joining between noisy GPS readings from a variety of sensors. Current solutions typically include some combination of PubSub, stream processing, SQL, and NoSQL frameworks. In this context, PubSub and stream processing systems are well suited for working with streaming IoT data, while SQL and NoSQL frameworks often include spatial indexing and other features for working with spatial data. While there is a lot of current work in this space, to date we have found that there was not a single data management framework that could address all of the requirements of our AI-driven urban mobility applications and research. Therefore, we use this presentation to present our own experiences in designing a custom data management framework for AI-driven mobility systems. We identify 5 challenges in this domain. The first challenge is related to how we model and manage the data itself, and what type of infrastructure do we use to store it. As a research group, we focus on open source data management technologies. In this work, we discuss our own design decisions and our thought process as we implemented our data architecture. Second is data synthesis and stream processing, which is how do we join and process the real-time data streams. The various domain-specific schemas and spatial components of urban mobility data present unique challenges related to map matching and spatiotemporal data joins. Third is efficient data retrieval, which is largely related to supporting efficient spatiotemporal queries and data sharing between groups. Also, as we manage data for multiple agencies, how do we define access rights to each data source? Therefore, secure access mechanisms were an important design decision for our team. Fourth, our system aggregates and stores data from many sources. Therefore, we wanted to include mechanisms for identifying failures and anomalies within our framework. We consider this a problem of monitoring. Lastly is how do we make the data available in an easy way for operations teams, particularly non-technical teams. We decided to include a set of visualization dashboards which allow easy access to our data using predefined queries accessed through a website online. We made the site publicly available so other research groups or residents of Chattanooga can be engaged in our work. This presentation is primarily related to data collection methods for the fixed line transit system in Chattanooga, Tennessee, which is managed by CARTA, the Chattanooga Area Regional Transportation Agency. CARTA manages a mixed fleet of 50 diesel, 3 electric, and 7 hybrid vehicles that service their fixed line bus transit system. These vehicles are equipped with telemetry kits from our partners, VeraCity and Clever Devices. Readings from the VeraCity kits are specific to the type of vehicle. For example, electric vehicles record state of charge, battery current, and voltage, while diesel and hybrid vehicles provide fuel level and fuel consumed information. All VeraCity kits include GPS, which allows us to track a vehicle over time. Clever Devices kits also provide GPS information, but are additionally connected with the scheduling software used by CARTA, and therefore include which trip each vehicle is servicing. As CARTA does not have a real-time GTFS feed, the Clever Devices data allows us to map vehicles to which trip they are serving in real time. Fixed-line transit passenger feeds come from three sources. Automatic passenger counters, or APC, data comes from infrared lights at the vehicle entrances. APC data includes both boarding and alighting events. Fairbox data is derived from the payment processing systems on each vehicle. This data only includes boarding events, but through our experience has proven to be more accurate than the existing APC system. Many vehicles are also equipped with video feeds. External data for the fixed-line transit system includes weather from dark sky, traffic from HERE and INRIX, as well as high-quality elevation data from the Tennessee Geographic Information Council, or TNGIC. Scheduling is recorded in static GTFS format, and road network information is in OpenStreetMaps. Our data management framework primarily consists of a pub/sub layer implemented with Apache Pulsar running on VMware at Vanderbilt, and a persisted MongoDB cluster in Google Cloud. Real-time data is streamed directly to the pub/sub level, and each message stream is accessed by a three-tier naming scheme. The first tier is a tenant, which is the owner of the data. Access rights to each collection of message topics is granted at the tenant level and is provided natively by Apache Pulsar, which is one of the main reasons we chose this particular pub/sub framework, as we manage data from multiple agencies. The second tier is the data class, and the third tier is the data source. Connectors were designed to continuously read from the various data sources and write to the MongoDB backend. MongoDB was chosen for its support for highly unstructured data, as well as its native support for arbitrary geospatial indexing. The applications our group works on are AI-driven applications. In general, historical static data sets used for training can be accessed from the MongoDB data store. The monitoring applications and the visualization dashboards are also heavily reliant on MongoDB. At inference time, the real-time AI applications typically read directly from the various topic streams in Pulsar, which minimizes latency. Rather than relying on external stream processing framework such as Apache Spark, we rely on Pulsar's native support for stream processing. While Pulsar stream processing support is not as robust as frameworks designed specifically for stream processing, we found that the additional programming overhead outweighed the costs associated with managing a separate stream processing framework. An example streaming join is shown in this slide, which outputs a stream using a variety of our AI-driven applications discussed later in this presentation. In this example, we join real-time telemetry, weather, and traffic data streams with static OpenStreetMap and GTFS scheduling data. We write the resulting stream to a new topic in Pulsar, which allows us to see a vehicle as it traverses a scheduled trip. The output stream was used in energy prediction models designed to predict energy consumed by a vehicle over a trip, as well as offline and online optimization programs for scheduling vehicles to trips. One problem we often have to deal with is map matching. This is the process of tracking a vehicle trajectory over time and identifying which streets or segments that vehicle is on. In the above example, taken from a previous work of ours, we mapped the bus vehicle trajectory to OpenStreetMaps. As seen, the GPS readings from the vehicle are noisy. While map matching is a well-studied topic outside the scope of this presentation, we often find ourselves implementing various approaches to this problem in our data architecture. For our work, map matching is implemented as a stream processing function in Pulsar. Currently, we are using a custom approach outlined in the paper referenced on this page, though we are currently investigating additional approaches for this work. As part of this project, we have made two dashboards for the operations teams at CARTA. The dashboards were implemented with Python, Plotly, and Dash running on Google App Engine. The interfaces use MongoDB queries to present and investigate the available data we have collected. The dashboards are made available to the public at smarttransit.ai, so other research teams and residents can be involved in our work. The first available dashboard is the energy consumption dashboard shown on the slide, which summarizes the energy consumption of the various vehicle classes in CARTA's fleet. We provide a set of interfaces for aggregating this data at the system level, allowing users to query based on vehicle class, route, time of day of week, etc. We also designed an occupancy dashboard which allows users to analyze boardings and occupancy along spatiotemporal lines. This dashboard has helped operations teams quickly gain insights on how their fixed line transit system is used and to identify areas for improvement. Since the start of COVID-19, this dashboard has helped identify heavily used routes and other components of the transit system where social distancing and other requirements must be maintained. We made this dashboard available for both Chattanooga and Nashville, Tennessee. Components of this dashboard help guide our work studying the effects of COVID-19 on public transit in these two cities, referenced on this slide. Through this dashboard, users can investigate their own queries using our data sets. A nightly email system was set up to monitor data quality. The monitoring applications identify discrepancies in the number of messages that day compared to expected number of messages from historical data. These anomalies are summarized in email to help identify when various sensor streams or APIs are down to ensure we can address issues promptly. One example monitoring application is related to the status of VeriCity's telemetry kits. For this application, we first gather all vehicles that are actively serving a scheduled trip, which is obtained by the Clever Devices stream. We then check the incoming VeriCity streams for each vehicle and ensure we are obtaining data on each parameter at the expected frequency. Using this system, we have been able to identify issues with telemetry kits on specific vehicles and schedule maintenance accordingly. Currently, our monitoring systems are focused on verifying the quantity or number of messages on each data stream. We are currently working on expanding this to include looking for anomalies within readings themselves, i.e., when specific components are generating values outside the normal distributions seen in the past. Previous work of ours was on designing energy prediction models for electric and diesel fixed-line buses. The figure on this slide is taken from that paper and shows the relationship between each of the feature classes in the model and model performance. These models relied on the data collected and processed in our framework. Additionally, we have done work on optimizing vehicle trip assignments to minimize energy consumption of the fixed-line transit system in Chattanooga. This work was presented earlier at AAAI. We are currently working on including the optimization program in our energy consumption dashboard for CARTA. This way, CARTA can start to incorporate expected energy demand in their scheduling process and thus start to reduce the effects of their fixed-line transit system on the environment. Future AI-driven work includes creating ridership estimation models to help predict ridership patterns across different routes. We hope to extend that work to include smartphone passenger guidance applications so users of the transit system can make travel decisions based on availability on vehicles, which has become increasingly important during the COVID-19 pandemic. We are also working on proactive optimization of fixed route transit services. This includes looking at ways to maximize transit accessibility while reducing crowding on vehicles. One aspect of that work includes optimizing paratransit services and better integrating these services with the fixed-line transit framework. Our works are described in greater detail at smarttransit.ai. Thank you for your time.